Hello, this video is going to be on electric charge in electrostatics. So, what is charge? Well, charge comes from a transfer of electrons, and a force can be exerted when there is a net difference in charge or a net charge between two different objects. And this force is attractive or repulsive based on the signs of these charges. So, like charges will repel, and different or opposite charges will attract. So, when you have something like, say, a positive charge and then a negative charge, these two will attract. So, these are net charges. While if you have a negative charge and a negative charge, or a positive charge and a positive charge, they will repel. But the magnitude of the force between them, as we'll see later, only depends on the magnitude of the charges and not the signs of the charges. So between these, this should be attracting. So between these like charges, the charges will repel each other. So these will go apart. The force will be in opposite directions. Well, the force is always in opposite directions because of Newton's third law. But in this case, they will be pushing each other apart. And then for like charges, uh, the forces will, so the particles will be pushed together because of the attractive force between them. So charge here has units of coulombs. So coulombs, this is the unit for charge, and it's C is the abbreviation you use. And then charge has a variable of Q in equations. Another thing about charge is that it can only be in integer multiples of the elementary charge E in nature, which means that charge Q can only ever equal n E, where E is the elementary charge. So E is equal to 1.602 times 10 to the negative 19 coulombs. This isn't an exact number, there's more precision that you can get, but this is a good approximation. And then N here can be equal to like plus minus 1, plus minus 2, so it can be any integer. So positive or negative, but it has to be an integer multiple of this elementary charge. And so this can be viewed as the charge of an electron, or a charge of a single proton. So charge of a single proton. So in the case of an electron, it's negative. So this is really the magnitude. This is the magnitude of the charge of a single electron or a single proton. And so far, we have not observed anything that has a fractional multiple of the elementary charge. So you can only have integer multiples of charges from electrons and protons. And so, yeah, charges that are fractional multiples of this do not exist in nature. Charge also is always conserved, and so like if you think about it, the number of electrons and protons that you start off with has to be the same as the one number of electrons and protons you end up with by conservation of mass too, or conservation of energy, however you want to think about it. But charge is then also conserved. So now let's get into how materials work with charge. So you can have conductors and insulators for certain materials. So if a material is a conductor, that means that electrons move freely throughout the material. So conductors are like metals So like let's just say copper, brass, or steel. Those are all conductors, which means that electrons they aren't bound to a certain position or a certain spot inside the material, and they can move freely throughout the entire material. Whereas for insulators, so insulators here, uh, electrons cannot move throughout the material. They remain at the location where they're deposited or where they're originally at. So uh, electrons stay in place, basically. And then insulators, you can think of like wood or uh, glass or a lot of plastics or things like that where they don't conduct electricity, and so electrons can't move throughout the material. And then uh, there's different ways to charge these conductors or insulators or create a net charge on them. So whenever you rub objects together, there's friction, and then friction can cause a net charge to be produced. Now, in the case of insulators, when you say rub like a balloon against your hair or rub I don't know, a glass rod against silk, there's friction there, and then that causes electrons to be deposited from one material to another, and that creates a net charge. And since they're insulators, the net charge that's created stays in place. Um, but for conductors, let's just say you rub a piece of copper pipe on wool. There's still a charge that gets created when you're rubbing it from the friction. But since your copper is a conductor, the net charge doesn't stay in place because um, like let's just say you're touching the copper, then if there's a net charge, electrons will flow from the earth into through you into the copper to neutralize that charge, since copper is a conductor. And so while friction does induce a charge on or friction does create well, friction causes a net charge to form between objects. Conductors don't hold that charge, while insulators do. And when I say that electrons can flow from the earth through you to the conductor to neutralize that charge, whenever we have a connection to earth, that's called being grounded. So grounded yeah, is a connection to earth. And now Earth can be viewed as a practically unlimited supply or receiver of electrons. So if you have something that has a negative charge and is connected to Earth, then electrons can flow out of the object into Earth, and then that can neutralize the charge. Or if you have something with a net positive charge that's connected to Earth, then electrons can flow from Earth to that net positive charge to neutralize it as well. Um, and so, yeah, when you have a connection to Earth, the Earth can either donate or accept basically an unlimited amount of electrons, and that is what being grounded is called. Okay, so another important concept that you need to know is polarization. So polarization means the separation of positive and negative charge in an isolated object under the influence of a nearby charged object. So basically separation of positive and negative charge. Now what does this look like? Well, this can either be macroscopic or microscopic, so large and small scales. So macroscopically, when you have like a conductor, so let's just say you have a copper pipe here again. So this is a conductor. And then you have some positively charged object right here. So this positively charged rod. Now this positively charged rod, the positive charge comes from more protons being inside this material than electrons, because electrons were transferred out at some point. And protons are from the nuclei of atoms. So let's just say you have this positively charged rod here, and then it's right next to this copper pipe. Now, since copper is a conductor, you'll have positive charge, a net positive charge on this end. Sorry, you'll have a net negative charge on this end because the electrons will get attracted to the positive rod. So you'll have electrons grouping up in this end of it, since electrons can flow throughout the copper. And then the other end of the copper will have a net positive charge. So the copper becomes polarized because this end of the copper has a net positive charge, while this end, the other end of the copper near this rod, has a net negative charge because of the flow of electrons. Now, this can also happen on a microscopic scale. So let's just say you have a balloon and then you rub it against your hair, and then now it can like attract a piece of paper. So like this is really big, but cause when you rub a balloon against your hair and you like put it against a piece of paper or like pepper, like it attracts these. Now the paper itself is not a conductor, so it cannot polarize in the way that copper can. However, you can have individual molecules inside this paper, so atoms inside the paper, and they can become polarized. So the molecules inside the paper can create positive. I'll draw this bigger. So molecules inside this paper here, as you say, the balloon is negatively charged. Molecules inside the paper can polarize to where the molecules align, where their positive ends are going to be facing towards the negatively charged balloon, and the negative ends are going to be facing away. So basically, this would be like the electron cloud surrounding the atom would get pushed to where the electrons are on the opposite side, and then the nuclei of the atoms are going to be closer to the negatively charged balloon. And this causes the paper to attract to the balloon when it's charged. So this is where molecules or atoms themselves become polarized, whereas in the macroscopic scale, it's the entire object that can become polarized. So normally this would be randomly scattered, and so there would be no polarization, and there's no organization of the charge or the direction of the molecules and their charges inside an insulator. But when they're brought up against the influence of an externally charged objects, the charges inside the molecule or inside the material, even if it's an insulator, can align like this individually to where it creates a polarization. Whereas in the macroscopic scale, the electrons themselves can move to a different location to create this net charge and polarization. Now, there's different ways to create a charge in an object. And when I say create a charge, I mean produce a net charge. So charges can't actually, like I said before, be created or destroyed. It's always conserved. But you can produce a net charge on an object from having an imbalance of positive and negative charges. And so you can charge things by contact through conduction, or when you physically like when the two things are physically touching, they can transfer charges. So let's say in the example before, or if you have a positively charged like copper rod here, or let's just say you have a positively charged ball, and then you have a neutrally charged ball, and then you bring these together. So you bring these into contact. When they do come in contact, the charge, so when they do come in contact, the charge will transfer through this point of contact to where there's an even distribution of charges in both of these like conductive spheres. However, let's just say you have a case where, all right, this is by conduction. Let's just say you have a case where you have a positively charged, like, pipe. So this is positively charged. And then you have a negatively charged insulating rod. So you have this rod here that's negatively charged, but it's an insulating rod. And you bring them into contact. Now, since it's an insulator, when you bring this rod into contact with this positively charged conducting pipe, the charges inside the pipe can move around, but the charge inside this rod cannot. So only the point of contact can get neutralized. So in order for you to neutralize this entire rod, you have to like sweep or wipe the rod, the length of the rod against this other charged object, so the entire rod can become neutralized, because since it's an insulator, the charge cannot like spread out throughout the insulator to neutralize it. So these are examples of conduction causing the transfer of charge. Now, charge can also be transferred through induction. So induction is where there is no contact. So no contact. Uh, and so this can happen when, let's just say, you have a positively charged rod here. So this is positive. And then we have, like before, we have this copper rod that gets polarized. So this is this copper rod here gets polarized. Now, if we connect this copper rod here to Earth, then we have our positively charged rod here, and then we have a connection to ground. So this is grounded, and this is the symbol for ground. That means it's connected to Earth. Now, like we said before, Earth has an unlimited supply of electrons. So the electrons can travel through this connection to the rod. And so they'll neutralize the positive end of this. And so this electrons will flow from Earth into this copper pipe. And then that means that when you remove this connection from Earth now, you'll have a negatively charged pipe, even though there hasn't been contact between this copper pipe and this positively charged rod here. So this is what charging by induction can look like, where there's no contact between the two objects, the two charged objects, but you can still induce a charge on one of them, even though you're not directly touching it. Now we will find a way to use math to explain the force between charges. So Coulomb's law is extremely important in this, because it gives you the magnitude and the vector form of it can give you the direction of the force caused by a difference in charge, or not even a difference, but from a net charge in objects. So through observations, from experimental observations before, we've established that force, so electric force, coming from charges is going to be proportional to the magnitudes of the charges multiplied together, divided by the square of the distance between them. So when you have like Q1 and Q2, and then you have this rate R here, the magnitude of this force is going to be proportional to the charge, and the magnitude of the charges multiplied together divided by the square of the radius. Now notice that this looks extremely similar to Newton's law of gravitation, where you have the masses multiplied together divided by this distance times a constant. And so if we write this out in an equation form, we have the force, the magnitude of force is equal to a constant K times the magnitude of Q1 and Q2 divided by R squared. Now, this constant K here is actually equal to 1 over 4 pi epsilon 0. So epsilon null, or whatever way you want to say it. Here, this epsilon null is called permittivity, and it is equal to, or it is roughly equal to 8.854 times 10 to the negative 12 newtons times meters squared over coulombs. Or sorry, it is equal to the units for this are going to be coulombs squared over newtons times meters squared. And this can be found through the speed of light, but that will be covered later. That's not necessary to know yet for understanding Coulomb's law. So plugging this in, we get that this constant K here is going to be equal to around 8.99 times 10 to the ninth power newtons times meters squared over coulomb squared. So notice that this is just the inverse of permittivity units because permittivity here is on the bottom. Now, you can use this to calculate the magnitude of forces caused by electric charge. However, there's also the vector form of Newton's or Coulomb's law, which can tell you the direction of the electric force. So this can be expressed as force 1, 2. So the force on charge 1, so let's just charge 1, and then this is charge 2. This here, well, the direction of this can vary, but this, let's just call it force 1, 2. So this can either be in towards the left or towards the right, depending on the signs of the charges, but I'll just draw it like this for now. We have force 1, 2, which is a vector. So again, this is the force on charge or on object 1 by object 2 is going to be equal to constant K, or 1 over 4 pi epsilon 0 times Q1, Q2. Notice how this is not magnitude. This includes the signs of the charges. So this is Q1, Q2. So Q1 and Q2 divided by R squared. So R12. Now, R12 and R21 here, since it's squared, the direction doesn't matter. Times the unit vector of R12. So this is the unit vector. And then that means that the magnitude of this is equal to 1. Now, this is the unit vector of R12. And now, what is R12? Well, R12 is the position of charge 1 with respect to 2. So this is kind of crooked. This arrow right here is going to be R12. So it starts at 2 and it goes to 1. So R12 is the position of 1 with respect to 2. And so the unit vector of this is going to be equal to R12 divided by the magnitude of R12. So another way you could write this is equal to 1 over 4 pi epsilon 0 times Q1, Q2 over R12 squared times R12 vector over R12 magnitude. and this gives the direction between of the force caused by electricity or electric charge and the magnitude. And so if you notice, when you have two charges that are the same sign, this term here will be positive. So Q1, Q2 will be positive when they're the same sign. Because if they're both positive, then it's positive. And they're both negative, then the negatives cancel. So when they're the same sign, then the force is in the same direction as R1, 2. So if the force is in the same direction, you can see that it causes these to go further apart from each other when they're both the same sign. So same sign. However, when they're different signs, then you see that this term here, Q1, Q2, is negative because the one of them has to be negative, one of them has to be positive. And so when they're different signs, the force is going to be in the opposite direction of R1, 2, which means that force, so these should be in the like perfectly anti-parallel, which means that they're in opposite directions, but this means that they get brought closer together. And so it's an attractive force whenever the signs are opposite, and it's a repulsive force whenever the signs are the same. Also, you can add these forces through the principle of superposition, which means that if you have multiple charges around one object and you want to calculate the net force from the on that object, you can calculate the force from each of the charges individually and add them together. So let's just say you have like this object here, or like you want to find the net force on this charge here. From like, let's just say you have one positive charge here and a positive charge here and a negative charge here. You can find the force on each of these individually and then add them together. Well, this should be a negative charge. So, and then add them together to get the net charge or the net electric force. Okay, now let's look at an example where we can calculate the electric force on an object. So let's consider that you have two charges here. So this is going to be the origin. And then you have Q1. So this is Q1, and then somewhere along this x-axis, you have Q2. And they're separated by some distance d. Now this you'll see actually won't matter much. This distance here won't be too important in our calculation. It'll obviously influence one of the answer, but we don't actually need it to calculate the net force, unless we want to do it with respect to one of, like the position of one of these. Now, let's just say we have a charged particle here. We have a charged particle, a small positive charged particle, and we want it to be at equilibrium. So basically, we want to find the point where the force is zero between these two charges. And so let's just say where along this x-axis can a positive charged particle be at equilibrium? So there's two cases which we can consider for this. First case is both of these have the same sign. So if both of these have the same sign, and again, we want to find the place where a positive charged particle like can rest between them to where there's no net force. So sum of force here equals 0. So this is Q1, Q2. We know that the force on this positive charge here from Q1 is going to be equal to, we'll call that F1, is going to be equal to K Q1, and we'll just call this Q here, divided by, we'll call this distance here R1, so R1 squared. and then this here is going to be R2. So force 2 here from the second charge is going to be equal to K Q2Q over R squared. And now, since they're the same sign, we know that they're going to be acting in opposite directions, because if we think if both of these are positive, then Q1 is going to repel this charge and Q2 is also going to repel this charge. So they're in opposite directions. Now let's just say if the charge was out here to the right of everything, then we know Q1 will repel it this direction and Q2 will also repel it this direction. So we see that this can't ever be in equilibrium. So that means the charge cannot be in this position. And if we consider that the charge is to the left here, this positive charge, then both of them will repel to the left, which means that this can also never be in equilibrium. So if we want to find a place with a net force of 0, we know that the charge has to be in between these two charges, as long as the two charges have the same sign. And so, since they're in different directions, we subtract the magnitude of the forces. So we have the net force here is going to be equal to, and then we can factor out a KQ. So we have Q1 over R1 squared minus Q2 over R2 squared. And we want this to be equal to 0. So what this means is that Q1 over R1 squared has to be equal to Q2 over R2 squared. Or you can write Q1 over Q2 is equal to R1 squared over R2 squared. So what this means is that if Q1 and Q2 are equal, then this charge is directly in between this small charge, positive charge here, we call it our test charge, is directly in between the two charges. However, if Q1 is greater than Q2, then we know that R1 is going to be greater than R2. So that means this test charge here is going to be closer to R2 than closer to Q2 than Q1. And then if Q1 is smaller than Q2, we know that it's going to be closer to Q1. So this makes sense, because if Q1 is stronger than Q2, then it'll have to be a greater distance away from Q1 in order for the forces to balance out. And this follows with the inverse square law we see with Coulomb's law here, because the force is proportional to the inverse of the square of the distance between them. Now let's consider a case where these two charges have different signs. So again, we'll put one charge here at the origin and one charge here someplace along the x-axis. And then they have different signs. And then we'll call this Q1, Q2. Now, let's assume that Q1 is going to be greater than Q2. So if Q2 was greater than Q1, we can just flip their locations, or set the origin on Q2 to make the one at the origin is going to be the one with a greater magnitude of charge. So this is referring to magnitude. Now, let's look at some limiting cases. Again, we're trying to find where a positive charge here will have 0 net force on it. So if the positive charge was really close to Q1, it'll either be strongly attracted or strongly repelled. And so net force can be, and then from Q2, we know that it'll be weakly attracted or weakly repelled. So we know that these can never cancel. However, since they're in opposite directions, if you have a charge here in between them, I'll put it in green. If we put our test charge here in between Q1 and Q2, we know that it's going to be repelled by one of them and attracted by the other one. So in either direction. But the force from these are going to be in the same direction. So that means that the net force can never be 0, because let's just say that this is positive and this is negative, then this one is going to repel this positive charge, and this Q2 is going to attract it. So the net force is in one direction. And if the signs are flipped, then the direction is flipped, but the net force is always in the same direction. Now, since we know that Q1 is going to be greater than Q2, the magnitude, if we put a charge to the left, Q1 is greater in magnitude and closer than Q2, which means the force from Q1 is always going to be greater than the force from Q2 here. So this can never be in equilibrium, which means that the charge has to be to the right of Q2 for this to be in equilibrium, because Q1 is a greater charge, so it has to be further away from Q1 to have the force from Q1 be equal to the force from Q2. Now, if we actually look at it, the equation we can use to describe this is going to be the exact same as up here, because we know that force from Q1 is equal to K times Q1 and then Q over R1 squared, where R1 is just this longer distance instead. So this is R1, and then R2 is going to be here. And then, so we know force 2 is equal to K Q2 over R2 squared. So since these forces are the same, the equation turns out to be the same, and we have that Q1 over Q2 is equal to R1 squared over R2 squared. And so this confirms it, because you know that since Q1 is greater than Q2, R1 has to be greater than R2. And the only way for R1 to be greater than R2 is if this charged particle here is to the right of both of these. And still be on the x-axis. Because if we put it in the middle here, we can have R1 and R2. We can still have R1 be greater than R2 if we put the charge between them close to R2, Q2, but then the forces will be in the same direction, so they'll add and they'll never cancel out. Whereas if we put it to the left of both charges, the forces will be in different directions, because one of them is going to attract and one of them is going to repel. And so the forces can cancel out and have the same magnitude. Okay, now another thing to consider is we just said that these have the same sign or different signs, but we never considered what those signs were and how it affects the equilibrium position. So only the magnitudes here we see affect the position at which this test charge will be at equilibrium. However, let's just say you have Q1 and Q2 are both positive, then both of them are going to repel this test charge, which means that if you displace this test charge a little bit from equilibrium position, it's going to get repelled back towards that equilibrium position. So let's just say that we displace it a little bit here, and this charge is positive, then this is going to have a net force, pushing it back towards the equilibrium position. However, if both charges are negative, then both of them are trying to attract this test charge here, which means that if you displace it a little bit from equilibrium, there's going to be a net attractive force away from equilibrium, which means that if both of these charges are the same sign as the test charge, then it's going to be a stable equilibrium because it returns to equilibrium after it's displaced. However, if both of these charges are different signs from the test charge, that means that it's going to be astable equilibrium, which means that if you nudge the charge a little bit away from the equilibrium position, it'll get attracted to either one of the charges instead of returning back to the equilibrium position. Now, in the case where there's different signs, let's just consider Q1 here is the same sign as this test charge. If Q1 is the same sign as the test charge, then if we displace this a little bit to the right here, so let's just say this is displaced to the right, Q1 is going to have a greater influence on this charge than Q2 because it has a greater magnitude. And so because Q1 has greater influence, if they're the same sign, it's going to repel it. And so there's going to be a net force pushing this charge away from the equilibrium position if it's displaced to the right. And then if it's displaced to the left here, we know that these two have opposite charges. And so Q2 is going to have a greater influence on this charge than Q1 because it's closer to Q2 now. So there'll be a net force pushing it towards Q2, which again is away from the equilibrium position. So that means that if this test charge in Q1 have the same sign, then it's going to be in astable equilibrium because it gets pushed away from the equilibrium position if it's displaced. However, if this test charge in Q1 have different signs, then when it's displaced a little to the right, Q1, because it has a larger magnitude, will have a stronger force on it, so it gets attracted back to Q1, which is in the same direction as the equilibrium position. And if this test charge is displaced a little bit to the left, Q2 will have the same sign as this test charge, which means that it repels it. And then since it's closer to Q2 will have a greater effect. So it's going to push its test charge back towards the equilibrium position. So this test charge here will be in stable equilibrium whenever it is in opposite signs with Q1, and will be in astable equilibrium whenever it has the same sign as Q1, considering that Q1 and Q2 have different signs. All right, thank you very much.